Hi, I'm Jason.
And I'm Yang. We are GPU driver engineers.
In this video, we will present how you can accelerate your game engine with Metal 4. This is the second talk in our four-part series to introduce the next major version of the Metal API. Before we explore Metal 4 games, please watch Discover Metal 4 for a thorough orientation of what Metal 4 has to offer. After this talk, watch Go Further with Metal 4 games to learn about incredible new Metal effects and Metal ray tracing APIs. And watch Metal 4 Machine Learning for a dedicated talk on integrating ML. Let's explore Metal 4. Metal 4 is designed for the modern game engine. Games like Assassin's Creed Shadows from Ubisoft draw incredibly detailed characters and landscapes to immerse players in fantasy worlds. They stream gigabytes of detailed geometry and textures, rendered with thousands of shaders to take advantage of all the computing power available with Apple Silicon. The games of the future will be even more demanding and will need a graphics API that scales up to the task. That's Metal 4. Metal 4 contains some important advancements in Metal for games. These include efficient command encoding and scaled resource management to speed up your hot path, as well as quicker pipeline loading to get your players out of loading screens into games. In this talk, my colleague and I will dive into how to best use these features. In every frame of your game, draw calls, kernel dispatches, blitz, and ray tracing work are all on the encoding hot path. Metal 4 encoding is designed to meet this challenge by being efficient and concurrent. Metal 4 unifies the most common operations into two encoder classes so that you can do more with each encoder. Command allocators allow you to explicitly manage your memory allocations incurred while encoding. Command buffers let you encode work across multiple threads. The Discover Metal 4 talk described how two encoder classes, render and compute, handle all the command encoding. To use them efficiently, you'll need to synchronize data dependencies between compute operations, as well as use attachment maps to remap fragment shader outputs. All compute operations, kernel dispatches, blitz, and acceleration structure builds can now be encoded in a single compute encoder. Without any additional synchronization, these commands run concurrently. This allows workloads without dependencies to make better use of GPU resources. If some commands in the past need to run serially due to a data dependency, you can express this using a pass barrier. This barrier ensures that the GPU waits until all previous blitz on this encoder complete before later compute dispatches begin. Here's an example of how to synchronize access from a blit to a dispatch. First, the copy from buffer blit updates buffer 1, so encode a pass barrier. Then you can encode a dispatch that uses the data in buffer 1. That's unified compute encoding. Do all your compute work in one encoder and use barriers to express data dependencies. Metal 4 has also updated render encoding. With color attachment mapping, you can now control the correspondence between a render pipeline's color outputs and the render encoder's attachments. Instead of binding pipelines to a fixed render target layout, you can provide a color attachment map. Then when you set a new pipeline, you can change the map instead of switching encoders. Suppose you have a metal pipeline with a fragment function that draws to 3 attachments. Without color attachment mapping, you would create a render encoder with 3 color attachments. The fragment function returns 3 color outputs, and the encoder directs those outputs to the corresponding attachments in tile memory. For the next draw call, you might need a pipeline that writes to a different set of outputs. Since the attachments are different, you would need to create a new render encoder to match the color outputs. With color attachment mapping, you don't need a second encoder. Instead, the render encoder has all color attachments needed by both pipelines. Then, the color attachment map translates shading output to specific attachments. To implement color attachment mapping, start by setting up a render pass descriptor that supports color attachment mapping. Then, create the full superset of attachments that will be used by the encoder. To configure which attachment the encoder will draw to, create a color attachment map, then set its remap entries. For each entry, set a logical index to determine the shader output, and a physical index to determine the attachment index. Construct these mapping objects before encoding, and reuse them each frame. When setting a render pipeline, also bind a color attachment map. If a pipeline draws to different attachments, you can switch to a different color attachment map. Color attachment mapping can significantly reduce the number of render encoders in your game. This will reduce encoding overhead and improve GPU efficiency by reducing the amount of render passes. Metal 4 also gives you more control over memory allocations. Command allocators allow you to reuse command buffer memory and avoid dynamic allocations while encoding. Allocator memory grows as you encode commands. Reset allocators once the associated GPU commands have finished running. Reset makes their command memory available for reuse in later command encoding. You can use multiple allocators to avoid blocking encoding while GPU work completes. When you encode on a new command allocator, it will allocate memory for the encoded commands. This command memory is the work that runs on the GPU, so wait until committed work completes before resetting. Once the GPU work is complete, reset the command allocator. This immediately marks its memory as available for reuse. To continue encoding while the GPU work is running, use a second command allocator. This lets you avoid blocking encoding on the completion of GPU work. It's important to reset a command allocator once its GPU work is complete. Allocator memory will grow to support encoding until it's reset. If you don't plan to encode any more work on a command allocator, you can release it to reduce your memory footprint. Command allocators aren't thread safe, so use different allocators for different threads. This is important as you parallelize your scene encoding. Metal 4 command buffers let you divide your encoding across multiple threads. In single-threaded encoding, you would encode a series of commands to one or more command buffers in sequence. Take advantage of Apple Silicon's powerful multi-core CPU and begin multiple command buffers on multiple threads, each with a different command allocator. You can use the improved flexibility of Metal 4's compute encoder to evenly distribute the encoding of blitz, dispatches, and acceleration structure work. When you've finished encoding your command buffers, you can submit them all with a single commit call. Metal 4 also allows you to commit multiple render encoders as a single pass on the GPU. Suppose you have a render pass that takes a long time to encode. By default, if you divide your encoding across separate render encoders, the GPU runs them as separate render passes. Each pass incurs overhead for storing and loading intermediate results. Metal 4 provides suspend resume options to merge multiple render encoders. Simply suspend a render encoder in one command buffer and resume it in another command buffer. Once you are done encoding the command buffers, submit them sequentially in a single commit call. Submitting the render encoders in one commit instructs Metal to merge the render passes. To implement this, create the first encoder with suspending options. Metal will merge this encoder with future encoders. Use a different command buffer for each encoder. The middle encoder has both resuming and suspending options. Create the final encoder with only resuming options. Commit all three encoded command buffers together. That's it. Your render passes are now merged. You can use Metal 4 to improve your encoding efficiency by reducing your encoder count, reusing your command memory, and encoding across multiple threads. To learn more about Metal 4 command encoding, please refer to the article on the Apple developer site. Now that I've covered efficient encoding, let's dive into efficient resource management. Metal 4 has some exciting new features to help you manage your resources at scale. Argument tables and residency sets allow you to scale your resource binding to thousands of resources. Metal 4 puts you in charge of managing your drawable resources and gives you control over dependencies. Queue barriers provide a way to express your resource dependencies at scale. Texture view pools and placement sparse heaps help you manage the memory required by large resources. Increasing the complexity of shaders often means that a bindless model is appropriate for the quantity of resources. With a single argument buffer, your shader can access thousands of resources, including buffers, textures, samplers, pipeline states, and more. But indexed bind points are still used for binding your root-level resources. Use argument tables to bind resources by index. While encoding, set which argument table should be used by the next draw or dispatch. These resources are available to shaders as indexed function arguments. At draw and dispatch time, Metal collects the arguments. This means that it's safe to set a new resource to a bind index between draw calls. A single argument table can be set on many encoder stages. Creating argument tables before encoding lets you move resource binding off of your critical path. you can attach one argument table to several encoders. Use argument tables together with argument buffers to scale your resource binding needs. The next step to accessing these resources in your shaders is to make them GPU visible. Anytime you need a resource on the GPU, add it to a residency set. This includes pipelines, buffers, textures, and drawables. Residency sets allow you to group many resources together and make them all visible at once. Either attach them to a command buffer being committed or directly to the command queue. If a residency set doesn't change much over time, prefer attaching it to the command queue. But if a residency set changes frequently, then attach it to the appropriate command buffers. It can take time to prepare large resources for the GPU. You can ask Metal to make a set's resources resident ahead of time. Prefer having fewer residency sets with more resources each. This improves performance by allowing Metal to process your resources in bulk. To learn more about residency sets, please refer to the article on the Apple developer site, as well as last year's talk called Port Advanced Games to Apple Platforms. With Metal 4, your control over resource residency also applies to your game's drawable surfaces. To send your game's rendered content to the display, you render to the drawable surfaces in a CA metal layer. Each metal layer maintains a dynamic residency set. Add it to your command queue to make all the textures in the layer resident. You only need to add the residency set once. CA metal layer will update it as necessary. In Metal 4, you also need to synchronize your rendering with the drawable. During each frame after getting the next drawable, encode a wait on the command queue prior to rendering to the drawable. Then, after you've committed the render work, encode a signal to the drawable on the queue. Call present to send your frame contents to the display once rendering is complete. To reduce tracking overhead, Metal 4 puts you in charge of synchronizing your resources. Earlier in this talk, I covered how to use pass barriers within encoders. Queue barriers, on the other hand, express a data dependency across encoders on the same queue. Barriers filter by metal stages. Each command in an encoder is associated with one or more stages of execution. For example, draw calls in render encoders generate both vertex and fragment shading stages. Apple Silicon GPUs batch all the vertex work together, followed by all the fragment shading work. Metal 4's compute commands correspond to dispatch, blit, and acceleration structure stages. It's important to choose appropriate stages to avoid over-synchronizing. In this example, a compute pass performs atmospheric simulation in a kernel dispatch. It writes the results to a texture in memory. The render pass draws the scene. The fragment shading requires the results of the simulation to blend with lighting, but the vertex work should be free to overlap with the compute work. To synchronize access to the simulation results, encode a barrier from the queue's dispatch stages to the render encoder's fragment stage. To implement this example, begin by encoding the dispatch on a compute encoder. Then, on a render command encoder, add a barrier after queue stage's dispatch and before fragment stage. After the barrier, you can encode draw calls. Metal ensures that any fragment stage work in the current render encoder and in future encoders isn't run until all dispatch stage work in previous encoders is complete. To help you find the best places for your barriers, the Metal debugger will show you their locations, along with which encoders and which stages they apply to. Use this to maximize concurrency while maintaining your data dependencies. To learn more about synchronizing your resources using Metal barriers, you can read through the full articles on the Apple developer site. Texture and buffer streaming allows you to manage the memory footprint for thousands of resources. Metal 4 allows you to efficiently stream buffers and textures. You can create lightweight texture views and manage your memory resource footprint with placement sparse. Modern games can create hundreds of texture and texture buffer views per frame. Texture view pools allow you to pre-allocate the memory required to contain all your texture views. Then, you can create lightweight texture views at any index in the pool. This doesn't incur any dynamic allocations, so you can create them while encoding. Use the texture view's resource ID to bind it to an argument buffer or to an argument table. Here's how you can implement this. Create a texture view pool ahead of encoding time. In this case, the created texture view pool has memory allocated for 500 texture views. When encoding, Set a texture view at the desired index in the texture view pool. Use the returned metal resource ID to bind your texture view to an argument table. Sometimes, the resources you need to bind can have a large memory footprint. Sparse resources are great for high-fidelity resources that may not all fit in memory at the same time. They decouple the resource's creation from their memory backing. With placement sparse, you are in control over how your resources get mapped to the pages of your heap. When updating memory mappings for your resources, APIs on the Metal 4 command queue allow you to synchronize these updates with other GPU work. The memory in a placement heap is organized as a sequence of tiles. You control the assignment of these tiles to your sparse buffers and textures. Provide sparse resources with memory by mapping byte ranges or pixel regions to sparse tiles. When creating a placement heap, consider the sparse page sizes that your resources will need. Larger page sizes have some performance benefits during mapping and unmapping operations, but will use more memory for padding and alignment. The heap will support all sparse page sizes up to the maximum you specify. This example chooses a 64 kilobyte maximum page size. Once you've created a placement heap, you can create the sparse resources. Creating placement sparse buffers and textures is done from a metal device, similar to non-sparse resources. For buffers, align the requested buffer size with multiples of a sparse tile size. The device provides a query to perform this conversion. Set the placement sparse page size when calling new buffer with length or on a texture descriptor. This property informs the metal device that a placement heap will provide the memory backing. When you first create a placement sparse buffer, it doesn't have any memory backing yet. You assign tiles to buffer ranges with update mapping operations. To assign tiles from a placement heap to a buffer, first, specify an update mapping operation. Provide the starting offset and length, and the tile offset in the heap to assign to this buffer range. Then, submit the mapping operation on a Metal 4 command queue. To learn more about working with sparse resources, check out the article on the Apple developer website. Another challenge for modern games is managing large libraries of pipeline states. For that, I'll hand it over to Yang.
Thanks, Jason. Modern games need to create thousands of pipelines to create complex and dynamic visuals. Loading many pipelines quickly is crucial to eliminating shader compilation stutters and reducing your game's load time. To load pipelines quickly in Metal 4, you can reuse your render pipeline compilations. You can also compile pipelines on device with a new level of parallelism. To go a step further, compiling pipelines ahead of time allows you to reduce your pipeline loading time to near zero. I will start by showing you how to reuse your render pipeline compilations with flexible render pipeline states. Let's say you're creating a city builder game where players can place houses around the map. When the player is deciding where to place a house, the game should render the house in hologram style, so it needs a pipeline with an additive blend state. The player places the house and the house starts building. To render the house with transparency, to show the building progress, it needs another pipeline with a transparent blend state. Finally, when the house finishes building, it will render the house with a third pipeline with an opaque blend state. You could compile these three pipelines with full state by providing the full pipeline configurations upon creation. Start with the vertex function and the fragment function, and the color attachment configurations for the opaque, transparent, and hologram houses. Color attachment configuration here means a part of the descriptor that affects writing fragment shader outputs to color attachments. This includes the pixel format of the attachments, the write masks, and the blend states. Create a render pipeline descriptor that references the vertex function, the fragment function, and the opaque configuration. With that descriptor, you create the opaque pipeline containing a vertex binary, a fragment binary body, and a fragment output part. By swapping the color attachment configuration in the descriptor, you can similarly create the transparent pipeline and the hologram pipeline. Most of the binaries in these three pipelines are the same, only the fragment output part is different. From a CPU timeline view, you compile the full opaque pipeline, then the transparent pipeline, followed by the hologram pipeline. The CPU spends a lot of time recompiling mostly the same pipeline, except for the fragment output part. With Metal 4, you can now reuse most of the pipeline compilation by first creating an unspecialized pipeline. Then use different color attachment configurations to get the final specialized pipelines you need. This can really save you a lot of render pipeline compilation time. To achieve the savings, first create an unspecialized pipeline. Start with the same descriptor, but instead of providing the actual color attachment configuration, set every field to unspecialized. To do this, simply loop through all color attachment descriptors and set pixel format, right mask, and blending state to their corresponding unspecialized values. The unspecialized pipeline contains a vertex binary, the fragment binary body, and the default fragment output part. The default fragment output works for some cases, but most of the time, you will need to replace it by specializing the pipelines. To create a specialized pipeline, start with the unspecialized pipeline and a new render pipeline descriptor. This time, set the color attachment configuration in the descriptor to the actual values you need. The specialized pipeline contains the corresponding fragment output, replacing the default fragment output. This new fragment output can be generated very quickly, so you don't need to go through the full shader compilation process again. I'll return to the example of specializing the transparent pipeline. Start by setting the previously unspecialized properties in the descriptor, enable the blending state, and set blending substates. The code here sets a pipeline to do pre-multiplied alpha blending. Then, instantiate the specialized pipeline using the new descriptor with the unspecialized pipeline. Your game may be creating thousands of stateful render pipelines. To maximize the load time reduction, create all your render pipeline unspecialized and specialize them later as needed. After doing that, you may notice there's a small GPU performance overhead. A lot of the overhead can come from unnecessary work from the shared fragment body. For example, if a fragment shader writes to 4 color channels and the color attachment only has 1 channel, the compiler is no longer able to optimize the unused channels. There's also a small overhead caused by jumping from the fragment binary body to the fragment output part. This overhead is usually small, but can be large in some fragment shaders. Identify those important shaders and compile with full state in the background so your player can enjoy both short load times and great frame rate. You can use Instrument's metal system trays to rank the most expensive specialized fragment shaders. To recap, here's how to best incorporate flexible render pipeline states into your game. Start by compiling every render pipeline unspecialized and specialize them as needed. If there's a noticeable performance drop, use Instrument's metal system trace to profile your game and identify important pipelines. For those important pipelines, compile a stateful version in the background and use it to replace the specialized version when it's ready. To learn more about flexible render pipeline states, check out this article at the Apple developer website. After reusing pipeline compilations with flexible render pipeline states, shorten your pipeline load time further by parallelizing your on-device compilation. Some games might use a single thread to load pipelines during gameplay. Here's the single compilation thread that builds the pipelines the game is about to use. And here's a render thread that runs the repeated frame rendering work, such as encoding. If the required pipelines aren't ready in time, the game can stutter. You can speed up pipeline loading by adding another compilation thread. The pipeline compilation finishes sooner. However, if you're not careful with thread priority, the game can still miss its present intervals. After setting the background compilation thread's priority to a value lower than that of the render thread, the hitch is gone. The player can now enjoy smoother gameplay. Here's how to add multi-threaded compilation to your game. Use the Metal 4 compilation APIs. The compiler is able to go even wider in Metal 4. You can either use Grand Central Dispatch or create your own thread pool, depending on which one fits your game's architecture better. No matter which one you choose, remember to set an appropriate priority. Metal will respect the priority of your compilation tasks. Grand Central Dispatch is the easiest way to issue your multi-threaded compilations. If you want the compilation to inherit the priority of the calling thread, you can use dispatch groups with the async methods provided by the compiler. Async methods are the ones with a completion handler. Metal will automatically execute these methods concurrently. If you want to customize the priority of your compilation, you can create a concurrent dispatch queue with a custom quality of service or QoS class. For pipeline pre-warming and streaming, we recommend you set it to default. To submit compilation tasks to a dispatch queue, you can invoke sync methods in block and send it to the queue via dispatch async. Sync methods are the ones without a completion handler. You can also create your own thread pool if this fits your game's architecture better. Use a maximum concurrent compilation task count property in Metal device as the thread count for a thread pool. Set the default thread count to 2, as this is a maximum concurrency in OSs that don't support this property. It is important to also set a proper quality of service or QoS class for our compilation threads to avoid starving other important threads in your game. Set QoS class to default for pipeline pre-warming and streaming. And that's it. You can now start sending compilation tasks to your thread pool. For more information on the best ways to parallelize and prioritize your pipeline compilation, check out these articles at the Apple developer website. Multi-threaded compilation on device can greatly reduce your compile time. To further reduce it to near zero, pre-compiling pipelines at development time is the way to go. To compile pipelines ahead of time, games typically use an end-to-end workflow. The workflow begins by harvesting pipeline configurations used in-game by running the game with some instrumentation. The harvested results are fed into the GPU toolchain to build GPU binaries. Finally, at runtime, the game looks up the pre-compiled GPU binaries to quickly build pipelines. Metal 4 makes it easier than ever to harvest your pipeline configuration online and look up pre-compiled binaries in your shipping game. In Metal 4, the easiest way to harvest a pipeline configuration is to serialize a pipeline script. A pipeline script is just a JSON formatted file. It contains a textual representation of the pipeline descriptors you create on device. Serializing a pipeline script is easy with the pipeline dataset serializer in Metal 4. Once you bind this object to your compiler, it will automatically record the descriptors for the created pipelines. Next, you can serialize these descriptors into a pipeline script. To create the pipeline dataset serializer, start with a descriptor. Set a configuration to capture descriptors. This informs the serializer to only track pipeline descriptors and reduces its memory footprint. Use a serializer descriptor to create the pipeline dataset serializer. Then, attach a serializer to the compiler descriptor you use to create the compiler. After creating the compiler, you can just use it to create pipelines as usual. The serializer will automatically record the pipeline descriptors you use. When you're done harvesting, call serialize as pipeline script with error to serialize the recorded pipelines into a pipeline script. The returned value is an NAS data. You can use your favorite method to send it back to your development system. This example just writes it to a file on disk. Set the suffix of the file to MTL4 JSON. This is the suffix expected by the GPU toolchain. Once you've harvested pipeline configurations, the next step is to build the binaries. Feed your pipeline configuration script and Metal IR libraries to Metal TT. It will output the GPU binaries packed in a Metal archive. Before you feed the harvested pipeline script to Metal TT, open the script and modify the path to the Metal IR libraries, match the path on your development system. For more information about the pipeline configuration script format, open the menu page with this command. Next, simply execute the Metal TT command on screen to build an archive for iOS. Now that you pre-compile the binaries, your game needs to look them up at runtime. Metaphor makes it even easier for you to create pipelines from GPU binaries in an archive. Just use the same descriptor you would use to compile on-device to retrieve the pipeline states. For example, create a Metaphor archive object by providing the URL to your archive. Then, query the pipeline state directly from the archive object with a pipeline descriptor. The lookup into the archive can miss for multiple reasons, such as no matching pipeline, incompatible OS, or incompatible GPU architecture. You need to handle such misses yourself in Metaphor. The example here simply falls back to on-device compilation, so the game still has the required pipeline state going forward. Here's the CPU timeline for the example game again with a multi-threaded on-device compilation. By adopting ahead-of-time compilation, the pipeline load time shrinks to almost 0. To learn more about ahead-of-time compilation, check out these articles at the Apple developer website. Here's a recap. Metaphor provides great ways to load pipeline states faster than ever before. You can reuse compilation results using pipeline specialization. You can further speed up compilation with multithreading. For the lowest pipeline load times, adopt ahead-of-time compilation with a streamlined harvest and lookup workflow. We were so excited to show you many ways to use Metaphor APIs to build the next generation of high-performance games.
Download the new Xcode to begin optimizing your game's encoding, resource management, and pipeline loading. We've included sample projects and detailed articles to support your journey.
To continue exploring what Metaphor has to offer, check out the other talks in this series. Thank you for watching.